Hello and welcome back. So in this segment we want to start to talk about how do we think that the solar system came into being. And so I wanted to start it off with a little bit of humor here. So if you want to watch this little video called Cosmic Scrat-tastrophe, this is from one of the Ice Age movies, and it explains how Scrat single-handedly was able to make the solar system. So if you want to watch it, go ahead. Alright, now we want to talk about the scientific explanation as to where the solar system comes from. Now this is going to be called the Nebular Hypothesis because we think that the solar system originally was a nebula, which is a big ball of gas and dust. So later we will talk about exactly what nebulas are when we talk about the formation of stars, but for right now we're just going to say it's a gigantic ball of gas and dust. And the gas is going to be 99% hydrogen and helium, and then it's going to be about 1% dust, and that dust is going to eventually become the planets and you and me. So we're going to say that approximately 4.57 billion years ago, you had a gas cloud that was 10,000 astronomical units in diameter. Now to give you an idea for how big that is, that's going to be about half the distance from our sun to the closest star, which is Alpha Centauri. So it was many, many times bigger than the current solar system. And so it's going to begin to collapse because of gravity. So gravity is always attractive and it's going to pull things in. So this gas cloud, which consists of trillions and trillions of particles of hydrogen and helium and dust, it's all going to start to get smaller and smaller. Okay, then the next thing that's going to happen is as it contracts, it's going to flatten into a disk. So remember that at the beginning it's going to be spherical, and then after this process is over with, it's going to be flat. So we want to be able to explain that. And so in order to do that, I have my orbital simulator here, which looks remarkably like a hula hoop, but let's pretend that what this represents is the orbit of the gas and the dust particles. So some of them would have been orbiting like this, meaning going around and around, because they were in the plane of the future solar system. But then some of them also could have been orbiting like this, which means that they were orbiting around and they made an angle to the solar system. And then you also had some of them that might have been orbiting like this, and possibly even some of them were orbiting, straight up and down. But due to collisions, they eventually flatten into a disk. So how is this going to happen? So if you've ever watched NFL football and you see that the quarterback has the ball and the quarterback is heading in this direction, but then you have another person like a fullback or some kind of a tackler, and they are lumbering in this direction, and then they collide with that quarterback, well, they tend to go in a different direction. So like, for example, if somebody is initially going this way, and then they bump into somebody that's going this way, well, this one will change their direction depending on how heavy this person here is and how heavy they are. So you can have different directions that they're going to go after the collision, but they're definitely going to change the direction that they're going in. So that if you've got a dust particle and gas particles that are orbiting like this, and then they collide with orbiting particles that are going like this, can you see that they might change their directions and eventually start to flatten into a disk? Okay, so collisions of the gas and the dust particles are going to cause this spherical gas cloud to collapse into a disk. Okay, now the next thing that's going to happen is this disk is going to begin to spin faster in order to conserve angular momentum. So if you recall, angular momentum was given by the letter L, and it was equal to the mass of a particle times the speed of a particle times the radius of the particle. So the distance that the particle is from wherever it's rotating from. So that the mass is not changing, it's the same particles. But if the radius is getting smaller, then what happens is the velocity is going to increase in order to compensate. So 1 times 4 is 4, but 4 times 1 is 4. So if one of these variables is getting smaller, another variable has to get bigger in order to compensate. And you still have the same m over here. So the m's did not change. So you see this with ice skaters. Just go to the internet, type in the word ice skater spinning, and you will see an example of this, that they're spinning around and they initially have their arms out like this, okay, but then as they bring in their arms, they're going to start to spin faster. So this disk is going to start to spin faster. Okay, but this disk eventually is going to stop contracting, and then that disk is going to form the solar system. So you might be thinking, well, what could possibly keep this disk from collapsing any further? Shouldn't all of this material just keep collapsing until you've got basically one star and nothing else? Well, there's going to be this thing called centripetal acceleration that is going to counteract the effects of gravity. So gravity is trying to take this disk and pull it in and turn it basically into just one single star and no disk. But what's going to happen is this disk is going to stop collapsing and is going to have a certain size, and then that disk will eventually become the planets in the solar system. So how does this work? Okay, you may be familiar with this concept if you're in a car and you're driving and then you make a sharp right-hand turn and then you feel as though you're being thrown outwards. So that's kind of an illusion, because what's really happening is you want to keep going in a straight line because of Newton's first law of motion, but the car door bumps into you, and so that gives you this feeling that it's the car door pushing on you instead of you pushing on the car door. Okay, now this is all related by this formula here called the centripetal force formula. So it's going to depend on m. So m is going to be the mass of the thing that's going around in a circle. V is going to be the speed of the thing that's going around in a circle. And then r is going to be the radius. So it's going to be the distance from the thing that's going around in the circle to the middle of the circle. Now think about this. The disk is collapsing, right? So what's happening to its radius? The radius is getting smaller. So look at what happens when you put a smaller number in the bottom part of a fraction. Then what comes out gets stronger. So this centripetal force, which has the effect of keeping the material from collapsing any further, is getting stronger. And then look at what the V is doing. The V is getting bigger, because think about the ice skater. When they bring in their arms, they start to spin faster. So the V is increasing. Notice where it's at. It's in the top part of the formula. So that means, again, the force, the centripetal force, is going to get stronger. So eventually, the inward pull of gravity is going to be counterbalanced by this centripetal force thing. And so now the disk is going to start to stabilize at a certain size, and now the planets can begin to form. So in our next segment, we're now going to start to sort out the solar system into those different kinds of zones. So the zone that consists mainly of rock and metal, and then the zone that consists mostly of gas, and then the zone that consists mostly of ice. So we'll talk about that in our next segment.